Well, this is a pretty good turnout for the 3-hour lecture. Just get comfortable. Okay, thanks everybody for coming. This is something that's a lot of fun to do. So what I'm going to be talking about tonight is the search for life beyond the solar system. And I'm going to talk about this in the context of a mission that NASA is studying right now called LUVOIR. Well, it's an acronym, but it sounds French. I'll tell you what it stands for as we go along. So this is the title of this talk. When people talk about the LUVOIR mission who are on the team, we don't use this full title. The thing that we use for LUVOIR is Big Bang to biosignatures. So that's supposed to encompass the goals of the LUVOIR mission, everything from finding the origins of our universe to finding the signs of life on planets outside the solar system. So I'm not going to talk about the Big Bang aspect tonight, but I will talk about biosignatures and finding life on planets around other stars tonight. Okay. So I'll start with a little bit of introduction, sort of where we are in the universe. At present, we are the only planet that we know to have formed and evolved life. We're looking elsewhere, but this is the only place where we know that life has formed. So despite that, of course, philosophers and theologians since the early times have wondered if we're alone, if we're unique in the universe, or if life, civilization, biology has developed elsewhere. Of course, this is a central theme of NASA's mission to search for life beyond Earth. Some places that NASA's actively looking for life. We are looking for life on Mars. This is one of the reasons why we send rovers to Mars. We're currently planning a mission to go to Jupiter's moon Europa. This is one of several ocean-bearing moons in the outer solar system. These are moons that we think have a crust of ice over top of probably what's a saltwater ocean. So this is another place that we're in the process of trying to understand if biology could have formed there. And then what I'll talk about tonight, which has become sort of a hot topic in the last 2 decades, are planets orbiting other stars, or extrasolar planets, and sometimes I'll say exoplanets. But basically this means any planet that is around a star that is not the sun. So before we get to exoplanets, though, I want to sort of step out from our place here on Earth. So we're one of 9 planets orbiting an average middle-aged star. Well, this is Boulder, and this is where we did New Horizons. So we have to continue to judge that Pluto is a planet for a little while longer. But if you are not in Boulder, or you're not working for the Southwest Research Institute, you refer to this as 8 planets orbiting an average. I know, I would do too. An average middle-aged star. We're pretty typical. Earth is around a typical star in a typical part of a typical galaxy. So the sun, this is our light source here, the thing that makes Earth habitable. It's about a 5 billion year old, very run-of-the-mill orange star. It's about halfway through its present life. It's not particularly active. It's a relatively peaceful place. And this is where we are. If we could imagine looking down on the galaxy, the Milky Way galaxy, this is where the sun resides, here between these 2 spiral arms, about halfway to the edge of the Milky Way galaxy. So again, there's nothing that puts us in a particularly interesting place. So there's a lot of reason to think that just on statistical grounds that we might not be the only one of us. So one of our driving questions now in modern astronomy is, are we alone, or is our solar system unique? So we've learned in about the last little over 20 years now, that we're certainly not the only planetary system in the universe. This has been sort of this kind of revolution in astronomy really was started in 1995, which was the first confirmed extrasolar planet around what I'll call a normal star, a sun-like star. It's this sort of famous 51 Peg B object. This was followed up a few years later by the first transiting planet. I'll talk about transiting planets in a second. A few years later, we got the first confirmation of atmospheres on extrasolar planets. So not only do we know that there are planets beyond the solar system, they do have atmospheres. This was some work done with the Hubble Space Telescope. And then in 2009, the Kepler Space Telescope was launched. And Kepler, incidentally, was operated right here in this building. Is it still operated in this? Is K2 is still operated in this building? Okay, so it's not hunting planets the way it used to, but it's still doing amazing science and is still being operated in this building. So there is the connection. So so Kepler really revolutionized the detection rate of exoplanets with several thousand planets detected as of today. So before we sort of dive into the next part of the talk, I want to do a little bit of background about how we find these planets in the first place. We have three primary detection techniques for finding extrasolar planets. So there's the transit method. This is what Kepler does. Essentially, you're just watching the light from the star, and when the planet crosses in front of the disk of the star, the light dims. And so we watch this characteristic dimming event, and if it happens on a repeatable period, we believe that this is a planet. We check for other false positives like other stars or other potential explanations. And we do find some false positives, but by and large, most of the stars that show this signature are confirmed to have extrasolar planets. So we can also do this with instruments on ground-based telescopes and to a lesser degree on space telescopes, where we can block out the light from the central star and find planets glowing in the excess light beyond the star. So this is sort of a direct imaging technique. This is rather challenging to do for any planets other than really large Jupiter planets that are pretty far away from their parent stars today. But this is the technique we'll talk about tonight for finding Earth-like planets in a little bit. And then the other primary planet detection technique is what we call a radial velocity technique. This is essentially we use the gravitational tug of the planet on the star to detect the wobble in the star caused by the gravitational interaction of that planet. So we use essentially the Doppler shift. So when the planet is on that side of the star, we get a blue shift, and when the planet is on this side of the star, we get a red shift. And we plot those out, and we see this characteristic sinusoidal shape that tells us that there is a planet tugging on that star. So put all together, we now know as of a few weeks ago when I started writing this talk, that there are about 3,700 confirmed extrasolar planets known today. So if you compare that to the number of extrasolar planets we know of in, say, 1999, that's about a 185-fold increase. So we are detecting planets at a breakneck pace. So for reference, there were about 20 extrasolar planets known, and this is about the time when I graduated from college. So extrasolar planets were not in my college textbooks, but now they vastly outnumber the number of planets we have in our own solar system. So this is impressive, right? A factor of 185 in about 20 years. If we go back to our comparison with the solar system has lost 11% of its planets since 1999. So you'd like to study the thing that's going places. Okay, so one of the things that we found about when we've started to assemble these large samples and do demographics is that most planetary systems look very different than what we have here in the solar system. So if we plot this up, the different types of planets versus their number, and this is size. I hope you can see this in the back, but these are Earth-sized planets right here in this bin. And then for reference, these are the planets that we have in our solar system. And you can see that nature has decided to make the two most common types of extrasolar planets things that we don't have in our solar system. So these are the things that we call super-Earth planets and sub-Neptune planets. And they fall between Earth and Neptune. And these are by far the most common types of planets in the universe, but we don't have any. So that sort of interesting on the face of it. I want to talk about just two examples of types of planets that are kind of extreme things that we don't have in our solar system. So the first types of extrasolar planets that were detected were these hot Jupiter planets. As the name suggests, they are like Jupiter and they are hot. They're hot because we find them in these extremely short period orbits. So we find these Jupiter-sized planets almost about 50 times closer, 50, 40 times closer to their parent star than we are to the sun. So these things are absolutely getting baked. So much so that we think that they're losing their atmospheres. Essentially, their atmospheres are getting boiled off at an extreme rate. In fact, we've detected signs of these evaporating atmospheres with the Hubble Space Telescope. Again, this is something that was not expected. Theories of how you form planetary systems don't predict these types of objects, and yet these were the first planets found around other stars. The other thing that we found a lot of now that we didn't expect were these super-Earth planets. And by super-Earth, I mean things that are a few times the mass and a few times the size of Earth. This is just one example, Gliese 832c. So this is a planet that has about 5 times the mass of the Earth and is about twice the diameter. And it orbits at distances that might make it actually candidate for liquid water on its surface. But there are reasons to think that this might not be a good liquid water candidate. So what we're ultimately interested in astronomy, I think sort of the holy grail for exoplanets, is finding the potentially habitable planets. So we'd like to find the planets that may have the ability to host life. And this is just an artist's rendition of one. So what do we mean when we're talking about potentially habitable planets? Well, astronomers typically talk in the concept of the habitable zone. You may have heard it referred to as the Goldilocks zone. This is the orbital distance where liquid water can survive for some fraction of that planet's year. In the solar system, we live in the habitable zone happily. But if we were around a different type of star, the habitable zone would be moving around. So here is the inner solar system. We've got Venus, which is in the red zone here, a little too close to be habitable. There's Mars on the outer edge, a little too cold to be habitable. But if around other types of stars, like more massive blue stars, the habitable zone will move outward because the star is brighter. So you can be further out and still have liquid water. So Mars could be habitable in some other planetary system. And similarly, if we look at a fainter red star, that star is less luminous than our sun, so the habitable zone is going to move inward. So in this other solar system here, something at the orbit of Venus might be a habitable planet. So this concept of the habitable zone depends on what type of star we're orbiting. For us, if you're interested in sort of the nitty-gritty details, for us here, we're orbiting something called a G-star. That's like the sun. And we are at 1 astronomical unit. And 1 astronomical unit is just the separation between the Earth and the sun. If we went to the next most massive star, bluer stars, F stars, they'll have habitable zone distances around about 2 astronomical units. And if we go to red dwarfs, M stars, they have very, very close habitable zones, about 1/10 of the habitable zone we find here in the solar system. So we'll talk a little bit more about planets around red dwarfs in a second. Okay, so what we want is we want to look for the signs of life on planets where we think life could have evolved. And we have a very geocentric view of this because we don't know what life elsewhere might look like, so the thing that we look for is what we know. We look for we look for the conditions that we think support life here in the solar system as at least a starting place. Okay, so we've talked about the background for finding planets in the first place. So what I will argue tonight is that the next 2 decades are going to be the time for the detection of biologically active planets around other stars. And there are a few ways that we can do this. I'll talk about some relatively near-term experiments that we can do to look for signs of life on other stars. And then I'll talk about LUVOIR, which I really think is the way we're going to solve this problem. So you may have heard of the James Webb Space Telescope. It was supposed to launch in 2018, and then it was 2019. And then actually, after I'd created this slide, I then had to add this question mark because there are ongoing issues about the launch preparations for James Webb. So James Webb is probably going to be a good instrument for searching for habitable environments specifically around red dwarf stars. I don't want to spend a lot of time on James Webb, but the idea is that James Webb is an infrared telescope, and so it observes in sort of longer wavelength light where M dwarfs are brighter, and so it's pretty well suited to work on red dwarf planets. The other place that's going to be good for looking for red dwarf planets in the next, say, 7 or 8 years are what we call extremely large telescopes. These are 30-meter diameter telescopes that are being built from ground-based sites. So this is the European version. So they got the European reference point being built in the Chilean Andes. There's also the 30-meter telescope, which is primarily a US-led effort. Maybe you've heard about this. This is the telescope that was supposed to go on the summit of Mauna Kea, and then there was a fair amount of concern from the native Hawaiian populations that this was not a good idea, so they were going to move it somewhere else, and then they were going to move it back. And right now I think they're back to Hawaii. But sort of the time frame here for building these large ground-based telescopes is sort of the mid-2020s. So these planets are going to be good for finding water on other rocky planets, but they're not going to be particularly well suited for finding what we think of as the signs of life, things like ozone and molecular oxygen and methane. They're not really set up with the right combination of sensitivity and instrumentation to do that even for red dwarf or planets around red dwarfs, but certainly not for planets around sun-like stars. So this is, I'll try not to show too many super technical graphs here, but if we look at the solar system here and we zoom in on the inner solar system, this is the Trappist One System. I don't know how many people are familiar with the Trappist One System. Yeah, so this was the red dwarf where they found 7 planets. I think it was announced about 18 months ago. 7 planets, 3 of which were in the habitable zone of that red dwarf star. But this cartoon actually really shows you how close in the habitable zone is around a red dwarf star. So I think it's E, F, and G are all in the habitable zone around this TRAPPIST-1 planet. So even to detect sort of rough signs of life on these types of planets would require 30 to 90 transits observed with the James Webb Space Telescope. So each of these transit periods is a few days, so 30 to 90 times. It becomes years of observing time that would need to be invested to find the hints of life. And these are planets around red dwarfs, not planets around sun-like stars. So I would take a rough stab and say that we might find 3 plus 1 minus 3, so somewhere between 4 and 0 inhabited planets with the James Webb Space Telescope. And I'd say it's probably a comparable number for those large ground-based telescopes. So I think if we're going to want to detect inhabited planets on a large scale, we're going to need a bigger instrument. We're going to need something a little more ambitious than James Webb, and that might frighten you a little bit. But so I think we're going to need something like this LUVOIR mission. So LUVOIR stands for the Large Ultraviolet Optical Infrared Surveyor. This is essentially, like I said, we call this Big Bang to biosignatures. So it has 2 focuses. One, to study the origins of the universe and how the universe has evolved. And the other is to find the signs of life on planets around other stars. Specifically, planets around stars like our sun. So we're really looking for Earth twins. We're looking for Earth 2.0 with LUVOIR. So as I also say, it's a space telescope in the concept in the tradition of Hubble, right? So by that we mean it's sort of the true successor to the Hubble Space Telescope. It has a comparable wavelength range as the Hubble Space Telescope. It's designed to be serviced by either robots or astronauts the same way that the Hubble Space Telescope was. So we really imagine this as the sort of the space observatory for the 21st century. Okay, so what does LUVOIR do different than an observatory like James Webb? So James Webb observes things in transmission, in transit spectroscopy. And again, remember, we're always interested in the spectrum of the planet because that's how we detect if there are organic molecules and ozone and things like that there. Whereas what LUVOIR does is a direct detection technique. So it looks for reflected light off the surface of the planet. Now that sounds easy. The challenge is that there are those pesky bright stars that those planets are orbiting. So if we take a sun-like star and put an Earth-like planet around it, it turns out that that star is about 10 billion times brighter than the planet that's orbiting it. So it's a real needle in a haystack challenge because this means that you have to detect one planetary photon for every 10 billion stellar photons that come in. That's a hard thing to do. So there's a lot of technology work going on, and I'll talk about this really briefly. But what we want to do is basically suppress the light from this bright host star and get back to an image that looks something like this, where we've blocked out the light from the central star, and now we can begin to see the orbiting planetary system around it. So this is the technique that LUVOIR uses. It uses a big telescope to provide high angular resolution, so you can separate these things out from their stars. It uses a big telescope because these objects are faint. I'll talk about how faint in a second. And it uses a very specific instrumentation known as a coronagraph to block out the light from that central star. I'll talk a little bit more about those things as we go on. So after we've taken an image of that pale blue dot, that Earth-like planet, the next thing we want to do is we want to assess its potential to host life. So again, how do we do that? We take a spectrum, because all of the signatures of Earth are essentially found in its spectral fingerprint. So what are the things that we're looking for when we take the spectrum of an Earth-like planet? Well, we're looking for blue skies. So this is an effect known as Rayleigh scattering. This is why the sky is blue on Earth. We're looking for things like molecular oxygen. We don't believe that we could have molecular oxygen in the abundance that we have here in Earth's atmosphere without photosynthesis. So we think this is probably a good tracer of photosynthetic activity on the surface of other planets. We'd like to know that that planet has the conditions for habitability, so we'd like to see features like water vapor in the atmosphere of that planet. We don't know that you can make life without water at this point, so this is one of the things that we're looking for. And then, we'd like to see more specific signs of advanced biology, things like methane in the atmosphere of these planets. So again, methane is not something that you would find in the atmosphere of Earth if we did not have thriving surface biology. So, is this possible? Can we go out and can we suppress the starlight by a factor of 10 billion and then take a spectrum of that object and see if that planet is hosting life? Well, yes, we can do that. So here is a simulation of the LUVOIR instrument. This is essentially, to put you in reference, I'm going to show you this cartoon spectrum, but in an actual simulation that has a full instrument in front of it. And so we can see the signs of oxygen and water, and there's some carbon dioxide in there. We do run into some problems at longer wavelengths here because the telescope is warm, and so we do get a lot of background emission from the telescope. You can talk about making the telescope cold, but that becomes very, very expensive. So we're trying to stay away from that. So this is for a planet at 30 light years using our large LUVOIR telescope, 15 meters. In about 96 hours of observing time, we can essentially find the signs of life in a planet around other stars. We can sort of do one better than that. We can also find the signs of life as a function of the evolution of that planet, right? This spectrum, it only represents Earth over about the last 500 million years or so. So there was about 4 billion years where Earth had biology but did not look like this. So we can use an instrument like LUVOIR to look for the differences between modern Earth, in the blue curve here, and say Proterozoic Earth before the great oxygenation event 2.5 billion years ago. And basically, again, if you have information from the spectrum, you can tell what stage of evolution these planets might be in. So this is pretty critical. So we not only have to suppress the starlight and image the planets, we then have to take spectroscopy to believe that we're really seeing the fingerprint of life. Okay, so what are the things that we're going to look for with LUVOIR? So if we look over this 0.2 to 2.5 micron part of the spectrum, we get access to all of our favorite tracers, all the oxygen species, water, carbon monoxide, carbon dioxide, methane, all the things that we think we're going to need to have a pretty good confirmation that what we're seeing is life. So this sort of says the same thing. And the other thing that is unique about LUVOIR is its ability to take an ultraviolet spectrum. This is the UV in LUVOIR. Take an ultraviolet spectrum of the host star, because this allows us to actually calculate the photochemistry in the atmosphere and make sure we're not getting duped by false positive events, essentially chemistry masquerading as life, abiotic chemistry masquerading as life. So all of these things have been built into the LUVOIR concept. Okay, so that's the encouraging news. Unfortunately, Earth-like planets are very, very faint. So this is an image of the Hubble Ultra Deep Field. This is the deepest image of our universe ever taken. This is over several hundred orbits of observation with the Hubble Space Telescope. And the Earth 2.0 at 30 light years is fainter than anything in this Hubble Ultra Deep Field by a factor of a lot. So, so we can do it, but it's going to require a really big telescope. And not just a really big telescope, but a really big space telescope, because we have to get rid of the effects of the atmosphere. We have to be able to work at very small angular separations from the stars, so we can actually resolve Earth and Venus and Jupiter, like in that image I showed you. And we have to have enough sensitivity to be able to take spectra of lots of Earth-like planets. And why do we want lots? Right? If we had, let's say, a 4-meter telescope, we could detect probably about, if you run through all the numbers, about 6 Earth candidates. And so you're going to take spectroscopy of 6 Earth candidates, and let's say you don't find anything, right? Well, it's 0 out of 6. So it's suggesting that there are no inhabited planets out there, but you can flip a coin 6 times and have it come up heads every time, and that doesn't mean that on the 7th time you're not going to find tails. So so with a small telescope, we really run the risk of doing this experiment but not coming up with a concrete answer. So if we ratchet the size of the telescope up a little bit, we go to 8 meters, now we're talking about 25 Earth candidates. And when we get to 15 or 16 meters, which is the size that we're talking about for LUVOIR, we're talking about 100 Earth candidates. And so this is basically just telling you, this filling in the completeness as we go farther and farther away from the sun, because we have bigger and bigger aperture. So when you've got 100 Earth-like planets that you're taking spectra of, all of a sudden finding none becomes very, very significant, and probably means a lot for our place in the universe. I think that what people would probably expect from 100 Earth candidates is something like 20 would probably show the signs of life. That's the expectation. So a large telescope gets you a large sample size, which gets you statistical confidence that we are either alone or not alone. Okay. So I mentioned it has to be big, but how big is big? So I measured it in something tangible, like the Chevy Traverse, and it turns out that the LUVOIR telescope is about 3 Chevy Traverses in size. So if you imagine 3 SUVs back to back to back, that's just the telescope. Then there's the rest of the instrument and the star shade and everything else. So this is certainly a technical challenge. There are a lot of things that we are working on now that we don't entirely know how to do. We're working on things like the deployment right now. This is something that we're building on the heritage from the James Webb Space Telescope. This is an animation of how LUVOIR would deploy in orbit. So it folds out. It has to fold up to get into the launch vehicle and then sort of unfolds as it gets out there. Deploys a sun shield to effectively act as a baffle, so you don't get stray light from the sun entering into the telescope. And then a critical thing that James Webb does not have, but LUVOIR will, are these modular instrument bays in the back. So I talked about being the tradition of Hubble. These instruments are designed to be removed and replaced with next generation instruments, say 5 or 10 years after the, every 5 or 10 years. And this is actually something that is required as part of, from Congress as part of this study, actually. So that's certainly not easy. There are a few other challenges. We currently don't have the ability to launch a telescope the size of LUVOIR. So we're waiting on the development of the Space Launch System. This is something that's being designed and built at Marshall Space Flight Center in Huntsville. The first launch of the SLS system is supposed to be in 2019, but then there's the sort of second generation Space Launch System that LUVOIR would use. So that's something that needs to happen to enable something like this. We need these high contrast observations that we talked about. So this is basically a challenge for doing these high contrast factor of 10 billion type observations. We've demonstrated this in the lab now. But the next thing to do is essentially build a space prototype for this and try it. So this work is ongoing now. We would like to build this coronagraph. The coronagraph for LUVOIR is called Eclipse. And basically the goal here, don't worry about all the words, but the goal here is to find that 1 part in 10 billion signal from the planet. So there are 2 other instruments that are going to be on the, or that are sort of notionally studied for LUVOIR. And that's going to be the segue into the last part of the talk where we talk about what we're doing here at LASP. There is a high-definition imager. So this is going to be the camera that takes the amazing pictures. You can think of this as the analog to Hubble. And then the LUVOIR ultraviolet multi-object spectrograph, Lumos. And the design reason for Lumos is to study essentially hot and cold gas throughout the universe. This is really important at early times, soon after the Big Bang, and understanding how stars form and die over the course of the life of the universe, as well as carrying out this important characterization of the host stars for our exoplanet observations. And so this Lumos instrument is the instrument that we're leading here at LASP. So we're actually the only university that's leading the design study for any of the instruments on, well, in fact, actually there are 3 other large telescope missions that are being studied right now. And LASP is the only place where there's a university that's leading one of the instrument studies. So we have a few needs to make this ultraviolet instrument possible. So we need some increases in sensitivity for our ultraviolet optics. We need better ultraviolet sensitive cameras. And importantly, and certainly relevant here at the university, is that we need the scientists and engineers, we need to train these people today because they're going to be the ones really doing the work as we get around to actually building this instrument in the next sort of 15 years or so. So how do we address all these things and sort of do this in a university setting? So we do it in the context of a suborbital sounding rocket program. So LASP has a long history of developing instruments for suborbital flights, from studying the sun to planets to objects beyond the solar system. So my group is the one leading the Lumos study for LUVOIR, and so we're doing a lot of the sorry, what's the word I'm looking for? The technology characterization is part of our ultraviolet rocket program. This is essentially a NASA-supported program that develops flight tests hardware for LUVOIR and other large NASA missions. We do this in the context of carrying out unique science experiments from rocket platforms, and in the process, we have a lot of involvement with undergraduate and graduate students that we essentially train to become NASA's next space science leaders. So I don't want to walk through everything we do in the program, but I would just want to give you a little bit of a flavor about how we sort of incorporate all these aspects into a typical sounding rocket mission that we do here at LASP. So I'll use the Suborbital Local Interstellar Cloud Experiment, SLICE, as an example. This is the SLICE payload sitting in my lab across the street. This was an instrument that we built and launched a couple of years ago on a NASA sounding rocket. So just to show you what are the components here and where each one of these pieces comes in, if we show a drawing with the full rocket skins on, so this is what our section looks like when it's ready to launch. It has these skins. For reference, that's about 11 feet long and about 1.5 feet wide. If we take those skins off, we see the instrument that we built. This is the thing that I showed you a picture of a minute ago. And all of this hardware is designed by CU engineers and students. And then all of it's put together by CU students. So if we strip this last layer away here, we can actually look at the instrument. Here we have a telescope in front that feeds one of these spectrometers, and the light's then recorded by an ultraviolet sensitive detector. So what are the things that are unique about this? Well, as part of this process, we're developing advanced, very sensitive coatings to go on these telescope optics. We're developing advanced detector systems to record the light from the object that we're looking at. And then we bring all this together, and the students and faculty here at the university run a series of tests and prepare this thing for flight. Let's see what happens here. That's the payload ray trace. Right. So after we've built up the instrument, and the students do a lot of the work on the calibration and work with vendors to develop the hardware, we take this instrument in its full built-up configuration. Typically, we go down to White Sands Missile Range. This is a picture of some of the NASA folks and some of our students who are these CU students here and here and here. And we integrate with the NASA subsystems, including the telemetry and the attitude control and the recovery systems. We build all these things up. It gets built onto a 2-stage rocket motor. This is a picture of the full vehicle sitting vertical. So again, some of the CU students here and me. This is on a 2-stage motor, a Terrier Black Brant. So this motor takes us to apogees of about 200 miles above Earth's surface. And but we don't stay in space. We just go up on a big arc and come back down. And we observe while we're at the top of the arc. And we get about 7 or 8 minutes of observing time while we're above Earth's atmosphere. So there's sort of a long process. We spend about a month out at White Sands Missile Range preparing for the launch. Again, to put it in context, this is about a little less than 60 feet long. So it's a pretty hefty rocket. This is the team just before I think maybe our last flight. This is Carrie Hoadley. She was a lead graduate student for our last flight. She had just taken the last remove before flight tag off of the instrument. These are the things that you don't want to leave on because your instrument doesn't work if you forget to take off the remove before flight tags. So this was a big moment for us. And then essentially the experimenters, the team from CU goes out and finishes their work. They send the NASA technicians in to arm the rocket. They essentially connect the self-destruct button that happens if the rocket looks like it's going to go off the range. They clear the personnel, and then a few minutes later, we launch. So this is a picture of launch from White Sands of that SLICE instrument. And here in the inset is an image of the real-time science display from the instrument on SLICE. This is basically taking spectra. This is our spectrum again that were acquired on a hot star during the SLICE mission. So while we're up, we are up for about 16 minutes. Again, we only take data on the top 8 minutes or so of the arc. This is where we land. This is how we fly across White Sands Missile Range. This is essentially the whole missile range in southern New Mexico. There's the famous White Sands National Monument. If you've ever driven across here, this is where they set roadblocks during rocket flights, and occasionally you'll get somebody who wanders off out into the dunes and can't be found, and they have to scrub the launch because we can't shoot rockets over people. But this is these are the dispersion circles for where we expect the rocket to land, and typically we land somewhere inside that first circle. So I want to show you about 2 or 3 minutes of a video from another LASP rocket. So I'm an astronomer, so we fly at night. So our videos are not quite as spectacular as a rocket that flies during the day because you see more. So I'm going to show you a video from another LASP rocket that's led by Dr. Tom Woods that is a solar sounding rocket. And I believe this will work. There we go. Now we've got it. So these are 2 views looking out the rocket. I don't know how loud this is going to be when it goes. Loud, maybe. Ah, there we go. Okay, so there's the ground camera on the right. And then there's the aft-looking camera on the left. So because this is a long, skinny pencil, it's not a very stable way to fly through the atmosphere. So we spin the rocket to increase its stability as it's going up. And that's what you're seeing there in this sort of vomit-inducing spinning picture here. Remember, we don't fly people on these. But the 2 motors burn. And eventually, you're not hearing the sound anymore because we've left the atmosphere, and so there's no sound transmitted any longer. So then they despin the payload. They essentially throw weights out from the payload the same way that an ice skater puts out his arms and slows down from the tight spin. This is the conservation of angular momentum. They open a door on the back of the payload, and this is, again, this is a sun-looking experiment. So there's some stuff that's flying by there. This is a sun-looking experiment. So what you're going to see is the payload is orienting to observe the sun. And then the side-looking camera is going to be seeing the Earth looking sideways here. And then once we're aligned on target, basically the attitude control system fixes the rocket in place, and it takes data for this 8 minutes as it goes over the arc. It's really pretty spectacular. I mean, it's very much space. You know, it's not sort of space. Like you're definitely in space here. Seeing this at night is very cool. On our last flight, we had a side-looking camera, and we took pictures of the West Coast as we went up and came back down. So you got to see Phoenix show up, and then Vegas and LA, and then everybody came back down. So after a few minutes, this is going to close up and re-enter Earth's atmosphere. And to protect the instrument, when it re-enters Earth's atmosphere, they spin it up like this to distribute the heat evenly during re-entry. So it doesn't have one side that takes the full load of the heat, because it's just aluminum, so it would make the aluminum very soft. Okay, and I won't make you sick this way again. Still spinning. But soon, we deploy a drogue chute. I hope it's soon. Okay, well, the drogue chute comes out. And then the full chute comes out, and we drift down towards the northern part of the missile range that I showed you in the last slide. And then the payload lands. So you can see the arroyos and stuff in the northern missile range here. And the payload comes in at about 30 miles an hour. It's worth it for the thud. Hang on one sec. So you can see the shadow that's coming in there. There's the rocket, and there's the parachute. all that in one big thud. Okay, and then they advance the rest of the gas after that. So that's what one of these typical rocket flights looks like. After it lands out in the desert, the experiment team and the NASA team goes out and recovers the payload. Again, this is Carrie Hoadley. She was our last grad student. That's Bobby Kane, who was a mechanical engineering student. we go find the payload. This was Carrie's first flight as part of her PhD. She got a little bit cockier for her second flight and insisted that if you were coming out on recovery with her, you were going to be a superhero. So this was her second PhD flight. Then we take these sections apart and load them onto a helicopter. Everybody feels very proud of themselves, and we bring the payload back, and hopefully in one piece when the parachute works pretty well, and we test it and bring it back. So this is a very short version of this, but basically this is try to give you a quick picture of how we use NASA's Suborbital Program, particularly here at CU, to fly new instruments. And essentially, the reason NASA likes this is because they can send us a relatively small amount of money, and we can decide what works and what doesn't work for them before they spend a whole lot of money on putting this in space on an orbital mission. And for us, this is actually, it's a very cool thing to do, but it's also probably the best training program for instrumentally inclined scientists who want to do space science going forward. Okay, but our primary mission, our primary technical mission here is to develop some of this instrumentation for LUVOIR. So I want to end just by mentioning LUVOIR for one more second here. So remember, we think from Kepler that 10 to 50% of stars have potentially habitable planets. We talked a little bit about James Webb Space Telescope and ground-based telescopes and how they probably won't really get the job done for finding life outside of the solar system, on a certainly on a large scale. And if we're going to find true Earth 2.0, right, the pale blue dot that Carl Sagan talked about, we're going to need an instrument like a LUVOIR. And so this study is in progress. NASA is supporting this study now. I'm a member of one of the science and technology definition teams. Like I said, we're doing one of the instrument studies here at LASP. This is a program that is being submitted to the National Academy of Sciences, and they're going to make recommendations on what NASA should invest in the 2020s. And if LUVOIR is the thing that they recommend, odds are that we will probably start building this mission in the next 4 or 5 years. When is it going to launch, and how much is it going to cost? I can't answer either one of those. I will tell you that it will cost more than a sounding rocket, and it will probably not launch until the mid-2030s would be my guess, given the time it takes to build a large flagship mission for NASA. So that's LUVOIR. What's CU's role? Well, so we're leading the science definition for one of the instruments, and we're doing the instrument study here. And then we're doing a lot of the technology development here on rockets, and I didn't talk about them today, but we also have a burgeoning small satellite program here at LASP where we do a lot of technology testing, and we train NASA's future leaders for space astronomy. So if you've got any questions, I'm happy to answer them, and thanks very much for coming out tonight.
When you were mentioning the size of the planets and you had that gap between the Earth planets and the Neptune size, and you showed those two categories in between, were those rocky planets or gas planets? Or?
Right. That's right at the transition between the biggest type of rocky planet that we think we can have, and then when you move into that sub-Neptune class, the other tall pole there, we believe that those are probably going to have atmospheric compositions more like ice giant planets. So the sort of up to about 1.4, 1.5 times the radius of Earth, we expect rocky surfaces can make it. But much beyond that, we believe that the way that they're formed, they essentially they pull in a big atmosphere early on in their lifetimes, and then that becomes something that looks more like an ice giant atmosphere.
Building off the previous question, what would the environmental differences with a super Earth be different from the current Earth? So how would a increased value of their G or whatever make the environment different?
Right. Well, once you get to be super Earth enough, again, you can't have a fully rocky surface anymore, and so we suspect that may be a non-starter for life. The larger gravity is probably not that much of a difference. We're only talking about differences in Earth's surface gravity by a factor of a few. The thing that's actually particularly challenging for a lot of the super-Earths that have been discovered now is they tend to not be in habitable orbits. They tend to be in very short period orbits, so they're probably inside of what we would consider the habitable zone. It's an open question and something that people think a lot about maybe super-Earth should be the first place we do search for life when we find them in the habitable zone. We don't know of too many in the habitable zone at this point, though.
I wonder how well studied are the spectral characteristics of biosignatures of early life on Earth?
That's a great question. So we know a fair amount about that in terms of the oxygen content in the atmosphere. And so I showed the one sort of pre-oxygenation spectrum up there. And so we think that if we look for different abundances of oxygen, we can sort of be covering our bases with looking for what we think of as modern biosignatures at the same time as looking for what might have been the atmospheric signature of a biologically active world prior to the current day composition. So it's something that geologists and biologists do spend a lot of time with, and slowly the astronomy community and the biology community is doing a better job of talking about these things, but it's a great question. So one over here, in the back.
On the graph, first question, where you said there wasn't a lot of Earth-like planets that were shown there. How does that change, or how does that graph skewed by our detection?
Right. So that is an excellent question. So the question was, what do our observational biases, how do they affect that picture? And so that picture is largely corrected for observational biases at this point. Out to a certain period, Kepler in its 4-year primary mission was able to get essentially a mostly unbiased view of planet occurrence rates out to a certain orbit. Things that are at longer period orbits basically did not go around enough times for us to characterize. But you bring up a great question, right? I showed those hot Jupiters at the beginning, or somewhere in the introduction stuff. And at the beginning of the exoplanet detection craze, all we were finding is hot Jupiters. And it turns out that, of course we were, because they're really big and really close to their parent stars, so they have this huge observational signature. But once we studied more and more, and particularly that's why Kepler was so important, we built the demographics, it turned out that those planets were only about 1% of all planets, even though they were the easiest to detect originally. So that graph that I showed will probably would not change very much now, even if we could say, make the sample size 10 times bigger.
What's the upper limit for how colossal you can make like an Earth-based telescope, other than like the point of diminishing returns? Like you said, it would increase your probability of finding planets quickly. When do you hit a wall?
For Earth-based telescopes? For like telescopes on the surface?
Yeah.
So for LUVOIR, the limiting factor is the launch vehicle, actually. We would have gone bigger if we could have. But we couldn't design something that we didn't think we could put into space. So that 15, 16 meters is kind of the sweet spot for realistic expectations about what the launch vehicle environment looks like in, say, 2030. On the ground, we're probably going to 40-meter telescopes sometime in the next 2 decades. Much bigger than that, it becomes an engineering challenge to maintain the surface quality over such a large surface, even when you do segmented mirrors. People have talked about something called OWL, the Overwhelmingly Large Telescope, as a 100-meter telescope. I mean, that's a football field. I don't know how realistic those things are, but the engineering challenges go up dramatically once you're bigger than 30 or 40 meters. Steve.
I'm not sure what's going to happen with the International Space Station, but have groups looked at assembling part of the telescope in the space station altitude and then go out further?
Absolutely. In fact, this is something that people see as a great potential synergy between the manned spaceflight program and basically NASA's Science Mission Directorate, is using an instrument like LUVOIR as a training ground for astronauts on their way to Mars. Let's go to, say, maybe not the International Space Station, but maybe, say, lunar orbit, and assemble some large fraction of this, and then move it out to its final observing place. That's something that a lot of people talk about, but the details are still a little fuzzy because we don't have a good picture of what the manned spaceflight program looks like in the next 10 years or so.
What, with the studies you're doing here, which NASA centers is LASP working with?
Right. So LUVOIR is being led by the Goddard Space Flight Center. It has involvement from, a pretty heavy involvement from the Jet Propulsion Lab as well, even though JPL is not really a NASA center. But they sort of act like a NASA center. But it's being led by Goddard. The other centers there, Goddard is leading 2 of them. JPL is leading 1, and Marshall is leading the 4th one. So those are the primary ones who are doing a lot of space science instrumentation, and so those are the ones that are leading the studies.
Considering the fingerprint of our solar system, the makeup of ours, are we considered the odd kid on the block in terms, because we're only looking at things that are observable, but is our composition considered to be like the odd?
Right. So that's a great question. This is a question about how nearsighted we're being by only looking for things that are like us. This is a challenge that I don't think anyone knows the answer to because we don't know what else to look for until we find it. So the thing that, my answer to this, I think, is that if we build something that is not narrow in scope, like a LUVOIR-like mission, we stand a really good chance of being able to find whatever it is that it looks like. If we build something that's looking for, this maybe a smaller version of this type of mission that's only doing, say, 1 or 2 biomarker signatures, if life is typically something else, we might miss it altogether. But if we, if we build something that is truly a space observatory for the 21st century, it's probably big enough in scope to answer questions that we haven't thought to ask yet. It's certainly been the story of the Hubble Space Telescope, is that, if you go back and, if you ask, Hubble has been in orbit for almost 28 years now. If you sort of lay out the top 10 science achievements of Hubble, maybe 4 or 5 of them were known, or they knew they were going to do that, and at least half, maybe more than half, have been things that were a surprise. And the only reason why we could do that is because Hubble's amazing, and it was so capable that it was actually able to answer questions we hadn't anticipated at the time of launch. And so I think the same thing's true here. All right, last question.
Are you collaborating with SETI Institute?
So SETI is not a member of this project. They're certainly part of the larger community team that's contributing science expertise to this study, but I don't believe there are any SETI Institute members specifically as part of the science and technology team for this mission in particular.
Okay, great. Thank you, Kevin.